I will go over 3 examples of hypothesis testing in this video. For each example, I will use the 4 steps outlined in previous video. Example 1. How much time do executives spend each day reading and sending emails? A survey of 196 executives was conducted, and the average time was 63.75 minutes. Assume that the population standard deviation is 21. Can we infer that the average amount of time spent by all executives reading and sending emails is different from 60 minutes? Assume at 5% significance level, that is alpha equals to 5%. The observation values in this exercise are time spent on emails, suggesting that the data are numerical or quantitative data. The first step involves setting up the null and alternative hypotheses. The research question is to make an inference whether the average spending time is different from 60 minutes. The population parameter is an average, so that is mu. It is typically easier to set up the alternative first. The alternative should be mu not equal to 60. As you can see, it is different from 60 minutes. If the alternative is mu not equal to 60, the null is going to be mu is 60 because they are completely opposite of each other. From the sign of inequality in the alternative that's not equal to here, we know that this is a two-tailed test. Not equal to means if it's much higher than 60 or much lower than 60. In the hypothesis test, we are looking for evidence in our data to prove that the mu is not equal to 60, either much more than 60 or much less than 60 minutes. Step 2. Step 2 is to compute a test statistic. Because the population standard deviation, sigma, is given to be 21, sigma is 21, the test statistic is going to be a z-score. If population standard deviation is not given to us, it's going to be a t-score. Over here, we know the population standard deviation is 21, so sigma is 21. We can plug all the numbers into the formula. For example, x bar is the sample average from your data of 196 executives, and the average is 63.75, so we put it here. And the mu 0 is the number occurred in the statements. So they are 60. So we put 60 here and divide by square root n. Sample size is 196. So square root of 96. After plugging all the numbers into the formula, we get a z-score, a test statistic, of a 2.5. We can also label the 2.5 on our bell curve as you can see here. So that's 2.5 z-score. And now it is right here, a z-score for 0 or 60 minutes. Depends on which scale you are referring to. Step 3. In step 3, we can use either a critical value approach or we can use a p-value approach. I'm going to start with critical value approach first. First of all, this is a two-tailed test. For two-tailed test, we have two critical values, also known as cutoff points. So one of them is positive, the other one is a negative. To determine where the cutoff value is, we can draw the bell curve. So we know there's a -1 to the left of 0. There's also a positive critical value to the right of 0. We're going to use the level of significance, which is given to us to be 5%. So this is a small corner to the left of a negative critical value. There's a corner to the right of a positive critical value. These two corners should add up to 5%. And using the symmetry of a bell curve, we know each corner should be half of a 5%. So that's going to be 2.5% or 0.025. If we do know this is a 0.025, we can find out that the z-score here should be positive 1.96 You can use Excel, you can use a Z-table to find it. If this positive critical value is 1.96, we know that the negative critical value should be negative 1.96. So two cutoff values plus minus 1.96. In step 4, we compare the test statistic, which is 2.5, with the two critical values, which is plus minus 1.96. If the test statistic is more than the positive critical value, that means if 2.5 is more than 1.96, we would reject the null. Alternatively, if the test statistic is less than the negative critical value, we would also reject the null. Because the null is right here, we are looking for evidence that our test statistic is further away from the null compared to the cutoff values. Our test statistic is 2.5, and the positive critical value is 1.96. So the test statistic is indeed more than 1.96. That means the test statistic, the evidence from our data, is further away from the null than the cutoff value. So we reject the null. What we have learned by carrying out a hypothesis test is that there is enough evidence from the data to prove that the average time spent by CEOs on emails is actually different from 60 minutes. Because we reject the null, so we take the alternative. The alternative says average time spent on emails is different from 60 minutes. We're going to solve this problem using p-value approach. Remember, the first two steps are identical. We just have to redo steps 3 and 4. In step 3, we need to compute the p-value, which is a probability between 0 and 1. This is a two-tailed test. We obtain a test statistic of a positive 2.5. The probability of a test statistic that is further away to the null compared to the test statistic is going to be the area to the right of 2.5. Because this is a two-tailed test, we would also have to consider the area to the left of a negative 2.5. Using the symmetry of the bell curve, we just have to compute one corner and then multiply it by 2. Using the norm.dist function, we find one corner is 0.0062. P-value is 2 times that, so that's a 0.0124. For a quick recap of norm.dist and norm.inf Excel functions, please click on the video linked in the upper right corner of this screen. In step 4, we compare the p-value with the alpha, which is the significance level. We always reject the null if p-value is less than alpha. So our p-value is about 1%, and alpha is 5%. So clearly p-value is less than alpha. We reject the null. And we are able to arrive to the same conclusion as that using critical value approach. That says the average amount of time spent by executives on emails is different from 60 minutes. Let's move on to the second example. The manager of a department store is trying to establish a new billing system for the store's credit customers. After a thorough financial analysis, she determines that a new system will be cost-effective only if the average monthly account is greater than $70. A random sample of 200 monthly accounts is drawn, for which the sample average account balance is $76, with a sample standard deviation of $30. Is there enough evidence at a 5% significance level to conclude that the new system will be cost-effective? The observation here in this exercise are monthly account balances. So they are numbers, and the data we are dealing with are numerical data. Research questions is to test whether the system is cost-effective, which is equivalent to testing whether the average account balance is more than $70. So the population parameter we have here is mu, and the alternative that's related with the research question is whether mu is more than $70. This is the equivalent of testing whether it's cost-effective or not. Because the alternative is mu is more than $70, the null is going to be mu is less than $70. So this is an upper tailed test because the sign of inequality for the alternative is greater than, so it is an upper tailed test. Step 2 is to calculate the test statistic. Because the population standard deviation sigma is not given, all we have is a sample standard deviation of $30. The test statistic is going to be a t-score, not a z-score anymore. We find the t-score to be 2.83. Let me show you how you can plug the numbers. First, the x bar is the sample average. Using the sample of 200 monthly accounts, we were able to find the sample average is 76. So you can plug 76 here. Mu 0 is the number occurred in the null and alternative hypothesis. That's 70. So we plug it here. Sample standard deviation is $30. We plug it here. And the last thing is going to be square root of sample size. That's the square root of 200. So we got a t-score of a 2.83. I draw a bell curve here. Note this time, this is not a z-curve. It is a t-curve. And with a degrees of freedom of 199, that comes from the sample size minus 1. That's 200 minus 1, 199. I also label the t-score equals to 2.83 on this curve. So right in the center is a t-score of 0. Our test statistic, the evidence from the data, is 2.83. First, solve this problem using critical value approach. This is an upper tailed test. So there is one positive critical value only, to the right of 0. We can find this critical value using significance level, which is given to us to be 5%. So that means the small corner to the right of critical value is 5%. We can find this critical value using Excel t.in function. T.in function takes two arguments. The first argument is area to the left. We know the area to the right is 5%, so the area to the left is 95%, or 0.95. The second argument is the degrees of freedom, that is 199. Using t.in function, we find the critical value is 1.653. I also label it here on this curve because the test statistic is 2.83, which is greater than the critical value of 1.653, we reject the null and conclude that the mean monthly account balance is more than $70. So the new system is cost-effective. Let's solve this problem using p-value approach. In step 3, the p-value for an upper tailed test is the area to the right of the test statistic, which we just found to be 2.83. Using Excel t.dist function, we were able to find the p-value is about 0.0026. In step 4, we compare the p-value with alpha. Remember, regardless of what kind of test we are doing, we always reject the null if p-value is small, especially if it is smaller than alpha. So our p-value is about 0.0026 and alpha is 5%. So p-value is definitely less than alpha, and we reject the null. So we arrive at the same conclusion as the critical value approach. That means the system is indeed cost-effective. Let's take a look at the last example here. We have 3 politicians, they are running for the Senate election. The result of a pool of 1,000 registered voters is summarized using this table. Do we have enough evidence to conclude the candidate A will receive less than 50% of the votes? Assume alpha is 5%. It is very important to notice that the variable of interest is the proportion of voters they are going to vote for A. And we are dealing with categorical data in this exercise. So we're considering voters whether they vote for A or they do not vote for A. So it's a yes or no. Clearly, it is a categorical data. In this exercise, we are only concerned with the proportion of votes received by A. So we can combine the votes received by B and C together. So A received 510 votes, whereas B and C together they received 490 votes. We are able to calculate the proportion of the sample who votes for A is 510 over 1,000. That's 51% or 0.51. And this is our p-bar sample proportion. The research question here is to see whether the population proportion of votes received by A is less than 50%. So the population parameter is P, not mu as the first two examples. The alternative question is to see whether P is less than 50%. So the null is going to be greater than or equal to 50% or 0.5. From the sign of inequality for the alternative, we are able to see this is clearly a lower tailored test. In step 2, we need to calculate the test statistic. Again, this is a categorical data. We are dealing with population proportion. You may remember the test statistic is always a z-score. Let's try to plug in the numbers into this formula. So first, for the numerator, we have a p-bar is the sample proportion. We were able to calculate that's a 51% or 0.51. P0 is the number occurred in those two statements. That's 0.5. So we plug it in here. For the denominator, we have P0, which is 0.5 multiplied by 1 minus 0.5 divided by the sample size of 1,000. Make sure you take a square root of that. And the z-score is calculated to be 0.632. Let's start with the critical value approach first. In step 3, we find a critical value. This is a lower tailored test. Lower tailored test always has a 1 negative critical value. This is 0. Critical value is going to be on the left. We also know that alpha is given to be 5%. So that means this small corner is 5%. Using this lower tailed probability being 5%, we can use norm.in function to find it. Norm.in function takes 3 arguments. The first one is the lower tailed probability, which is 5%. The second one is the mean. This is a z-curve, as you probably remember. For proportion problems, it is always a z-curve. We put a 0 here and a 1 as the standard deviation. We were able to find a critical value is negative 1.645. I also label it here. In the final step of the critical value approach, we compare the test statistic against the critical value. For lower the tail tests, like this example, we are looking for evidence the sample proportion is much less than 50%, which is at the center. So we only reject the null if the test statistic is to the left of this negative critical value. Our test statistic is a positive number. It is 0.632, which is greater to the right of this critical value of a negative 1.645. So we fail to reject the null and do not have enough evidence to conclude A is going to receive more than 50% of the vote. Let's take a look at the p-value approach. The p-value for lower tailored test is always the area to the left of the test statistic. So the test statistic is here. To the left is the big area right here. We can use the norm.dist function in Excel to find it. We were able to find the p-value is 0.7363. In the final step of p-value approach, we're going to compare p-value with alpha. Because our p-value is about 73%, we know it is more than 5%, so we fail to reject the null. And we arrive at the same conclusion as the critical value approach. That says we do not have enough evidence to conclude candidate A is going to receive less than 50% of the vote. There are more hypothesis testing problems along with their answers posted on our course site. Feel free to check them out. I have also several other videos where I worked out hypothesis testing problems using an iPad with a bunch of students online. They are linked at the very top of this screen. Feel free to check them out. This concludes the video, and I will see you in the next one.